Alright, so I'd like to try a little something different here. So, actually, we don't need that, but we're going to use polarizations quite a bit in the class in different parts. Either the polarization of an electret or the polarization of a magnet. In this case, I'd like to talk about the polarization on, or the induced polarization on this cylinder, on a similar cylinder to the one we've been talking about. And we're going to find that polarization, and we've already got an equation for that. That'll be fairly simple, although ugly. Then we'll use that to find the dipole moment, which is a little bit different. So the polarization sort of tells you which way the orientation of the atoms are. So it's like the dipole moment per unit volume. The dipole moment is going to be based on what happens to the charges in here, right? You're going to basically have an equivalent to, it's not exactly this way, but it's equivalent to it, having a bunch of electrons come down to the bottom, and that's going to leave a deficit of electrons on the top of your cylinder. So that's actually going to modify the electric field. So what will happen with that, I'll draw it here. What will happen with that is if they got a sphere and you had an electric field going up, what happens with the polarization is that the polarization, maybe not the best, but okay, the polarization pulls the field into the object and concentrates it like that. And that's how this guy is now interacting with the field. So that's actually changing the field around it. But it interacts with this field, and that's what brings it, that's what pushes it around. So what I'd like to find here is what is that polarization, and eventually get down to how much charge has accumulated down there, fake charge. So the first thing is just the polarization. Well, I gave you this equation. The polarization is equal to this thing called the permittivity of free space times this other thing called the susceptibility, which is related to the dielectric constant. We'll talk a little bit about that in later episodes. And then that's multiplied by the electric field. So what happens is, as you add more electric field, you get more of a polarization. Looks sort of like this. Polarization, electric field, straight line. That's it. All right. So this epsilon naught, this permittivity of free space, basically treating free space as it's a rock for the electric field to penetrate and move through. That is 8.854 Coulomb squared newtons per meter squared. It's actually farads per meter as well, but we're a long way from farads. The susceptibility for this material is 4. And then the electric field is the electric field we've been generating with this, which is 10 to the 5th. Here I said volts per meter, that's newtons per coulomb. Volts per meter equals newtons per coulomb. That's because I forgot to change that. I made an error somewhere, and I ended up trying to do things in a slightly different unit. Okay, so that's got an answer, right? That's 3.54, I think. Oh, 10 to the minus 12 here. 10 to the minus 12, 10 to the 7th, minus 7th? No, 10 to the minus 6, because I get another This is 35.4. Okay. Times 10 to the minus 7. All right, good. So we got this guy. Now we want to figure out the dipole moment of the entire thing. Remember, this polarization is just at like that point, or at that point there, or at that point there. It's basically the dipole moment per unit volume, which means to find the dipole moment, you take the dipole moment per unit volume, P, and then multiply it by the volume. It's incredibly tricky. And then you're done. Well, the polarization we just said was 3.54 times 10 to the minus 6 coulombs per meter squared. And then the volume is 1 centimeter squared times 10 centimeters. And this is 10 to the minus 5 meters cubed, which means we end up with 3.54 times 10 to the minus 11. This is meters cubed, coulombs per meter, I think. 3.54 times 10 to the minus 11 coulombs per meter. I'm doing okay. All right, so how much charge collects on the end caps? Question mark, right? Well, how did we get that? Well, remember, the dipole moment was just the charge on one of these end caps. So this end cap has a charge Q, this one has a charge minus Q, but it has a magnitude Q, times this distance that separates them from here to here. We want the Q, I think, right? So we have 3.54 times 10 to the minus 11 coulombs per meter equals this Q times whatever that length is, which is 0.1 meters. It's 10 centimeters. All right, so that means we have 0.1. So that should be, oops. Let's see, so that's 35.4 times 10 to the minus 12. Then I multiplied this by 10, so that's 354 times 10 to the minus 12 divided by m, so we just end up with C. Oops. Which is good because this is supposed to be the charge. So that's the right units. Coulombs, 354 times 10 to the minus 12. So let's just call that 354 picocoulombs. Not very much at all. All right? So to go through this and figure out how much charge is on the end caps, after I put this thing on the field, first I had to figure out the polarization, which included this 4, which is the susceptibility, which is a materials parameter. You have to look it up. After I find the polarization, I scale it by the volume. So the more volume with the same polarization, the more dipole moment you get. And I end up with a number. And then I'm allowed to use that number to figure out how much charge is on your end caps using this definition of the dipole moment. This is how the definition of the dipole moment is. If you had two objects, one charged plus and one charged minus, plus Q and minus Q, obviously, with a separation of L, then this is what you'd get. So that's what's basically happened here, is all the charges accumulated here. It's like having a charged ball separated from another charged ball. Gives you the same polarization. Or the same charge, the same, it gives you the same polarization, dipole moment. All right, well, thank you very much, and I will talk to you next time. Bye now.